Hello guys, welcome back to CFD College. I'm Ashkan and this is the second full tutorial of ANSYS Fluent. In this tutorial, I will show you how you can simulate uh, flow over a rotating circular cylinder. So the cylinder is circular in this tutorial, similar to the previous tutorial, but now in this example, the cylinder rotates, and we want to, examine how we can perform this simulation. In the next tutorials, we will have, for example, a square cylinders, and you will see that the situation is different in that case. And in such projects, we should use a sliding mesh, or you may know it as mesh motion, but it's not the subject of this tutorial. So in this tutorial, we will examine the simulation of a airflow over a rotating cylinder. Before starting the video, please subscribe this channel, share these videos with your friends, give us a thumbs up if you like these videos, if you find these tutorials useful, and I have many other tutorials on different phases of the numerical simulation, from pre-processing up to post-processing, like tech plots, CFD-Post, and so on. So it's good for you to check those videos. Uh, this is our domain. Since in this project this cylinder rotates, we need a bigger domain. So you can see the dimensions: 10D, 40D, 20D, and D is the diameter of the cylinder. In this problem, the diameter of the cylinder is 4 centimeters. The rotation speed is 100 RPM, revolution per minute. Working fluid is air, and you can see the density and viscosity. Uh, so first, let's create the domain, generate the mesh, and then we can think of, the flow, the inlet speed. Okay, this is my workbench. So I start with a block of Fluent. Then in this video, I'm going to use SpaceClaim instead of Design Modeler. It's good for you to be familiar with all these modules and choices: Design Modeler, ANSYS Discovery, SpaceClaim. We have, and even ICM. We have four modules in ANSYS Workbench for generating our domain. Okay, so since this is another uh, two-dimensional domain, we should work in XY plane. So you can just go to design, uh, new sketch. Okay, let me do this, and then again. Now we can create the sketch in XY plane. So if you click on this button, or press V, as you can see on your keyboard, you can look at the sketch perpendicularly. And let's go to File, SpaceClaim option to check the unit. The unit is millimeter, so it's okay, it's fine for us. Or let's change it to centimeter. It's better. So this is a circle, with a diameter of 4. Good. And now we can generate the domain and add some dimension. This one, the total length, uh, this length, and you can make it symmetric, or you can do something like this. And this is for the diameter of the cylinder. Now, all the edges are blue. It means that uh, there is no need to add any other constraint or dimension. It's already done. But it's 4 centimeters, so here we need 40. Mm, here is 10. Here is 40. Oh, sorry. This is 40D, so 160 centimeters, 40 centimeters, and it should be 20, so 80 and 40. So this is the domain, the CFD domain. So just click on return to 3D button, and you can see you have your domain. Press escape, okay, because we don't need to pull it. We want to work in 2D. In previous tutorial, I showed you how you should decompose the domain to generate a structured mesh. In this tutorial, I'll go with an unstructured mesh. So there is no need to decomposition of the geometry, but we have to create some names for the boundaries. So this is inlet. This is outlet. This wall are side walls, and this is cylinder. Sorry. So now everything is okay for us. You can close it, save the workbench, go to ANSYS machine, open the ANSYS machine. Unstructured grid. Uh, Actually, in a structure grid, in a structure mesh, you can't use inflation. So if you wanna create a boundary layer mesh, you have to do that using bias. If you haven't watched uh, previous tutorial, please watch that video and then come to this tutorial. These tutorials are made in a way that you learn something from in CFD, but you have to watch these tutorials step by step. Okay, but in unstructured mesh, you should create in boundary layer mesh using inflation in ANSYS machine. So view front. Okay, so here you need to add inflation for this surface on this boundary. And I use a first layer thickness. The diameter of the cylinder is 4 centimeter. So I need 20 layers, and the first layer thickness This is 1 centimeter. This is 1 millimeter. Let's see. Okay. Then I need to use face sizing. In structure mesh, we usually use edge sizing, and 1 centimeter should be fine. So now let's generate the first mesh, the initial mesh. Maybe 1 centimeter was too small. Let's see. Oh, so we should modify the inflation. So 0.0001. I think it's better. One, yeah, I think it's better. And then I will use an edge sizing for the cylinder. Modify this to hard and number of division. So 50 should be enough. Now let's see the grid. It's far better than previous mesh. How many cells does this mesh have? 14,000. So it's not much. As you can see, it's not, the mesh is not tetra. Tetra? No, tets. See here, if you add a method for this body, you can choose one of these options. Triangles, tetrahedron is in 3D. Triangles, or known as tets or tree, uh, quadratical dominant, or a multi-zone, which is a combination of quad and tree. Okay, so but the mesh that you can see here is a combination, I think. No, it doesn't. Yeah, it's here. We have a triangle, and I think we can find some others. If you want to have triangles, if you want to have triangle, you can change it to triangles. See that? See the effect? See? Here now we have triangular cells, and in the vicinity of the cylinder we have this structure boundary layer, and see the number of cells, it's 28,000 almost. So when you change the cell type from quadratical to tree, it's obvious that the mesh, the number of cells would be higher, almost double, not exactly, but it depends on you. It depends on you. Uh, it's not, I don't know, a rule that structure mesh is better or unstructured mesh is better. It depends on the project and the system that you have, because as you uh, saw, using with triangular cells, the number of cells is almost double, so the computational cost is higher. And okay, so you can modify this method to hex dominant, to quadrilateral, quadrilateral dominant. In 3D, it's hex dominant. Or multi-zone, it doesn't matter. Or you can delete it to have that quad cells. At least it's better because it doesn't need too much computation, and the view of the mesh is also better. So let's check the name selections, inlet, outlet, sidewalls, and cylinder. So everything is fine. Oh, I need to right click on that and click on update. You have to see this tick. Okay, that's perfect. So let me open the Excel file. Just a moment, please. Okay, now this is an Excel file. So density and viscosity are the same. Diameter of the cylinder is 4 centimeters. Reynolds number. Um, Reynolds number. Let's how much? For example, 2000, I think should be okay. Let's 200. Let's use 200. So we can use laminar flow in this Reynolds number, or we can choose 10,000. Now at least we know that flow is turbulent, and we can calculate the velocity based on this Reynolds number, which is 3.67. So let's open ANSYS Fluent. I always use double precision, and for this simulation I use 4 processors. It depends on your system. For example, if your system has 16 physical core, not threads. I'm not talking about threads. I talk about physical cores. Uh, so if the system has 16 physical cores, you may use 12 or 14. Never use all those 16 cores processors. Okay, so the flow, uh, it should be transient, and or let's say for the start, let's start with another situation. Let's pick 20 for the Reynolds number. So we are in laminar flow, and we can use steady state simulation for this. So the velocity is 7.35. So now we have steady state flow. There is no need to use turbulent models. So, and then we should modify the viscosity of the air. Next thing we have to do is to edit the inlet boundary condition. Let's see if we can copy it. Yes. Here in this tutorial, I'm going to use symmetry instead of uh, free shear wall. Outlet is atmosphere with gauge pressure of 0. You know why? Because we have a work operating pressure of 1 atmosphere. And cylinder is no slip wall. But we want to we want to simulate a rotating cylinder. Okay, let's start with a a stationary one to see the difference. Coupled is fine. Residuals, let's decrease them a bit to 10 to minus 5. Initializing the project. And start calculating for 100 iterations. But before that, let's create a monitor, a drag coefficient for monitoring the convergency of the simulation. So this is drag coefficient. Bring to console. This is the wall and start the calculation. See, the drag coefficient is constant here. Yeah, you can check it. Yes, the value is constant. So 50 iterations uh, were needed to have that convergency. And as you can see here, the drag coefficient gotten fixed. So you should always check some parameter as a monitor to ensure that the solution is converged. So now if you check the velocity contour, you can see this wake region. And if you check, let's say path lines, now you know that we need to create a line at, for example, 40 centimeter and minus 2 centimeters, 2 centimeters. So you should select both and color the streamlines by the velocity. See, we have two uh, stationary vortices behind the cylinder in the wake region. So now let's go to cylinder boundary condition, and instead of stationary wall, now we want to apply that rotation. Since here we have a circular cylinder, we can do it just simple as this. Open the boundary condition and change the wall motion type from stationary wall to moving wall. Now you have new option. You have to choose whether the motion is translational or rotational, or you can import the components. But here we have a rotational cylinder. You can see here we have to uh, specify two parameters: speed of the rotation and the rotation axis origin. Since the center of the circle of the cylinder is 0, 0. So x is 0 and y is 0. It's easy. But for the speed, the rotation speed is 100 RPM. So here you can see we should uh, convert it to radians per second, but you can do it. It's easy. Just Google it. But there is another way. Click on units, find angular velocity, and modify the unit from radians per second to revolution per minute. And that's okay. Click on close. See, the unit has changed. So it's 100 RPM. Apply, close, go to run calculation. You can do the uh, initialization again, but it doesn't matter. You can neglect it. So click on calculate again, check The residuals you can see here, convergency is not good because I think mainly it's because the speed of the rotation is too high with respect to the flow speed. So, and the drag coefficient is not fixed. So, when the speed of the flow is much smaller than the speed of the rotation, uh, you should have really big domain from sides, from up and down, or yes, that or since here, let's do the calculations for 100 iterations more, and let's check the velocity contour. See, the velocity contour has changed, and this is the streamlines. So it's obvious that the rotational speed is too high with respect to the inlet velocity. So let's decrease it to 10, and then we can use 100 for Reynolds number of 10,000. Click on initialize bottom, and then start calculate. See? Now it's like previous case. The drag coefficient is fixed, and it's only needed uh, actually 47 iterations are enough to do this calculation. Let's check the velocity contour. See, uh, this is the flow direction. This is the uh, direction of the rotation of this cylinder. So here the velocity is higher. The velocity is almost zero on top of the cylinder. If you wanna check velocity vectors, for example, first, and then we can check path lines, which are actually streamlines. I think something happened. Maybe the connection is lost. Yes, let me fix that. Okay, now the connection is okay, and you can see the vectors. Let me modify it to arrow and increase the skip. See, you can see the direction for the rotation speed of the cylinder. This is the flow direction, and here velocity is almost zero, but here velocity is increased because the rotation of this the two direction the directions of two velocities, the flow and the cylinder, are the same. Now for last thing, let's check path lines. See, yes, you can draw the cylinder. This is the cylinder, and these are streamlines. You can increase, you can't increase, you can, for example, modify the location of this line to see streamlines near the cylinder. Let's do that. Let's create, mm, let's create another line, 0, 0, and minus 2, which is here, a bit. So this is fine, and it should be fine. Let's add line 7. See, here you can see the path lines. The streamlines also. Actually, if you double click on the line, you can modify it. So let's increase the length of that line. It's better. Now you can see here, these are the streamlines and the streamline over all over the domain. So uh, this in this simulation, as you've seen, it's easy to, if you have a circular cylinder, it's easy to model the rotational, to add the rotational speed to the model. So it's steady flow. Reynolds number is 20, and omega is 10 RPM. Let's duplicate this block. So here for this simulation, let's increase both the rotational speed and the inlet flow speed. So Reynolds number is 10,000, so the velocity should be 3.67. And I think in this situation we will have vortex shedding, so we should use transient simulation. Since the flow is turbulent, if you remember, I showed you the different regimes of this flow in the previous tutorial. So K omega SST with this the default options. I think it should be good. I hope Y plus is fine. We can check it. You should check it if you are doing your thesis or I don't know, any academic or industrial project. This is just an example, an educational example. So K omega SST, and for the inlet, we have to modify the velocity 3.67. 3.67, and everything is fine. You just need to specify this autosave frequency, or you can create an automatic export. I explained these in previous tutorial, but again, if I want to say some words, we usually in transient simulations, we usually save data files because after the simulation, we want to examine the flow at different instances. For example, we want to report velocity, pressure, or contours or temperature contours at different instances to talk about them, to examine the flow. So you need to specify uh, an autosave frequency. For example, it depends on the time step. It depends on the space that you have on your disk. If you don't have much space and you cannot save many data files, you can create an automatic export. Here, for example, for CFD-Post, or if you are working with TechPlot, it's here, format I mean. And since here in this method you only select the quantities that you want, for example, pressure, velocity, magnitude, and something else, for example, velocity gradients, pressure gradient, or anything else, uh, the size of this export is much less than data file, so you can decrease the uh, data export data frequency. That's the point. Okay, so I don't need that because I don't want to make animation of these, but I think it's better to save the data file every 10 time steps. If you go to run calculation, the number of time step, I start with 100, the time step size. This is 4 centimeters. Uh, here is 40 centimeters, so half meter. The velocity is almost 4 meters per second, so the flow reaches the cylinder in about 1/8 of a second. So if I use 0.01 second as time step, I think it should be fine. And I increase it. I explained these settings in previous tutorial. So let's initialize the flow and let's see what happens. It's not good, but it's not too bad. Oh, sorry. I should uh, stop it. Let's just check the velocity contour. I forgot to increase the rotation. So we should increase it to 100. Initialize. I can reduce this a bit, but I think it should be fine for us for now. So just click on calculate to start the calculation. I think it takes a few minutes, maybe 15, 20 minutes for the simulation to reach the state that I wanted to show you. Let's stop the simulation and check the velocity contour. So now we have the wake, and it seems that I have to increase the rotating speed, but let's see what happens in few minutes, and then we can decide. So I think I pause the video and wait for the simulation to uh, reach somewhere. Let me check the velocity contour again, and then we can stop it and let it run for 300 time steps. So I pause the video, and in the end, we will see what we have. Hello again. See, now you can see the drag coefficient. This trend shows us that vortex shedding is occurring in the flow, and yes, now you can see the residuals. In transient simulations, the residuals should be like something like this. Don't afraid of that. So let me stop the simulation and let us check velocity contour. Now see you can see the vortex street, but the difference is now the drag coefficient is fluctuating around 0.6. If there was no rotation for this cylinder, this drag coefficient should be fluctuating around 0. But now, because of the uh, rotation of the cylinder, uh, the vortices are not, exactly similar to each other, and this causes this, the fluctuate. This causes the fluctuations. These fluctuations around 0.6, not 0, because it's not symmetric. These vortices are not symmetric in this simulation because of the rotation velocity. These are streamlines. And let's check velocity vectors. Now you can see that. So let's run this for only one other time steps. So this is the effect of rotation of the cylinder. Let me open CFD-Post. This view, symmetry 1. The color mode should be a variable, for example, velocity. Let's see what we have. We only have these quantities. You can create Z vorticity, but you need to use expressions. So if you want to learn about expressions and creating new variables, please watch the video which is related to that in CFD-Post playlist. The maximum velocity is 5.6. So let's decrease it to 5. I think this way we can. Okay, what about 4? Not 1, 4. I think it's good idea. Now we can see the animation. In this way, since we are working in the workbench, we can see this animation only by saving the data files. And the last thing I want to check is, let's save this workbench. Now let's go to solution. Solution is Fluent, but when you are working with workbench, if you open setup, all the data, all the previous data uh, will be gone. And it's like that you wanna do the simulation again from the scratch. But if you open solution, the data is already there. So it seems that you wanna see the data is there. So this way you can continue the simulation. So let's increase the speed of rotation to 300. This way, maybe we should reduce the time step size, but I won't do that for now. Let's see what happens. I think you can see the trend of drag coefficient is a bit different right now, and it should be because we have increased the rotational speed, so it should affect the flow. So let us see what will happen. Now I think the drag coefficient, the average value, I mean, is decreasing. You can test it. For example, increase the rotational speed to 1000 and see what will happen. Stop the simulation, go to contour, see that. Hmm, let's increase it more. It's interesting, no? So 600. At one point, I think it should uh, destroy this street, this von-karman street. Now, I think the effect of the rotation can be seen better. The drag coefficient is decreased to around, I think, 0.55. So now you can see the effect of the rotation on drag force, on the flow field, on the vortex shedding, and everything is going to be changed. And I think it's fine for this session. Just let's check whether to. I think we can't see so much difference by contour. Here you can see the maximum velocity of the flow is increased from 5.6 to 6.4 because the rotational speed is higher. And see this, a small vortex here, and here there is another one. Okay, good. I think it's fine for this session now. In this example, we had a good review of what we learned in previous tutorial, and uh, you learned uh, you learned new things, how you can uh, apply the rotational speed to a circular cylinder. Don't forget that this was a circular cylinder. In future tutorials, you will see that if the cylinder is not circular, for example, it's triangular cylinder, or if it's square, it should be different the way we have to use. It is named sliding mesh, and you will see that in our future tutorials. So Please, again, subscribe the channel, introduce us to your friends, share these videos with them, and give us a thumbs up. Thank you for watching this video. Until the next video and next tutorial, take care of yourselves and bye bye.